what we should do is go back to look at actually the very first definitions we had concerning terms and formulae. So let's go over those once again. So I've rewritten these here. It's on page 36 of the notes, beginning at section 3.3. So if we look at definition 321, yeah, I'll share my screen here with you. So the difference here that there's a small difference between how Charles set it out. I'm going to use as basic parts of our vocabulary, I'm going to use here not and implication arrows and for all symbol. He chose in definition 112 not and exists. But these are all interdefinable one from another. So there is no need to worry too much about that. But my definitions have been set out using not, arrow, and for all. So in definition 321, what do we see here? We define what the terms of a language, formal language, script L are. And at the same time, we'll define their complexity, which is just a number we'll associate to the term, which will tell us how complicated it is. So in the first clause here, we've got that a variable is something of complexity 0. Constant symbols in the language are going to have complexity 1. And if I've got a function in the language, and the arity of the function is n, it's an n-fold function, and I've got terms t1 up to tn, then I can apply the function to the terms. And what I then get is something, and its syntactic complexity is now, well, the maximum of the inputs that we put in here, plus 1, right? So we end up adding 1 each time we apply a function to the maximum of the terms of the inputs here. And this is the only way we build up terms. Right? So an example, if I've got a binary function f and a ternary function g, 3-place, and I've got some constant symbols, a and b, then here's the function f applied to a and variable v0. So according to the recipe above, the complexity is going to be the maximum of the complexity of a and that of v0. Well, constants have value 1 and variables 0. So we end up here with 2. G is a function applied to a function. This we've just argued, the f part has got complexity 2. V1 has got complexity 0, and b, another constant, has got complexity 1. So we end up with a maximum of 2, 0, and 1 plus 1 is 3. G of f applied again to f, if you look this up, this has complexity 4. G of AB is not a term because it's kind of been illegally formed. G is supposed to be a 3-place function, and there's only 2 inputs. So that's not officially a term. This one isn't a term because the function f here and the inside hasn't been applied to anything. Okay, now we do the same again for formulae. An equation is something that has got complexity 0. Okay. Sorry, I was just checking my hardware. A relation here, let's suppose it's an n-fold relation. And I put in terms, and I say the relation R holds of these terms. This is an atomic formula. Atomic formulae are ones that are complexity 0. So it's something really basic, right? So both equations, no matter how complicated the terms are, an equation's got complexity 0. And likewise, so is a relation, even if the complexity of the t's is very high. Adding a negation symbol adds 1 to the complexity. An implication has got complexity, the maximum of the two components, plus 1. And if we quantify a formula, again, this adds 1 to the complexity. And nothing else is a formula, an official formula, except you build it up using these clauses. So, as I've said, we can define exists in terms of for all. So let's just see then what happens. Let's see what happens here. So I've said I'm taking something like this here as basic for all vi phi. And perhaps phi has got complexity k. Now then the complexity of this has got k plus 1. Okay, just by those clauses that are there. Now, if I want to look at the complexity of this, right, so again, let's assume this has got complexity k. Officially, exists is the same as not for all not phi, right? Okay. So this has got complexity k. So this has got complexity k plus 1. Right? I put the for all on front. This has got complexity k plus 2. And there's another negation at the front here. So it ends up with complexity k plus 3. But that's only because we're choosing this as basic and we're defining exists in terms of for all. So you might think this is just slightly awkward, but it's not. It's only the only point of assigning complexities to formulae is that we can then define by induction some function or property on formulae and prove that it works. And likewise, if I look at phi, if I look at phi and psi here, this is going to be a shorthand for phi arrows psi, arrows psi arrows phi. Sorry, and psi arrows phi. So if I've got something of the form P and Q here, right? This is the same as not P or not Q here. Not P or not Q is the same thing as P arrows not Q. So P and Q is equivalent to, now this is something that's just written out using our basics. It's just using arrow and not here. So if I've now got then that, if I've now got phi and psi here, I can then say this is equivalent to not phi arrows not psi, right? Using these kind of equivalencies here. So what I've got then here is something, if this has got complexity k and this has got complexity L, right? And let's suppose for argument's sake that k is less than L, right? So this here has got complexity now, this has got complexity L plus 1. The larger of these two is L plus 1, so this here has got complexity L plus 2, and then one more up here at the front, it's got complexity L plus 3. Okay, so this is not a very big or complex idea here. So we build up our language using just not, an arrow, and for all here. And we can define our complexity for the formulae that are there. Now we also had the idea that a formula had got free variables, or variables were bound, perhaps in a formula. So the idea is that if I've got something like this here, this is an equation. I've got a constant symbol and I've got a variable here. So at the moment, it's kind of innocuous. If I were to interpret this in a structure, whether it were true or false in the structure would depend upon what I'd assigned to V0. If I assigned something that C was assigned to, then this would be a true statement. On the other hand, if I assigned V0 something differently to what the constant C denoted, it would be false. Right? So there's ambiguity here. This doesn't have any definite meaning. So when we come to interpretations, it's got no definite meaning yet. It depends on the assignment of V0. So, but something like this, or this, this no longer has a kind of free variable in it. This now has got very definite meaning when we come to interpret it. It says that our structure is, well, it's non-empty. It's got something that's going to be the interpretation of this C that we assign. So it says there is something. On the other hand, this statement here says everything equals what we assign to C. So it's going to say there's only one thing in the structure. But either way, right, there's no ambiguity here. These both have definite meaning. The variable that was free here has become bound by the quantifier. And the example that mathematicians always like to give is, they say something like this: we've got some function f of x and y, and we integrate with respect to dx. But so the dx here somehow binds the x that's in the f. We're integrating with respect to this variable. Right? But the y variable remains free. And x is bound. So the next algorithm that's there is, again, a repeat of an earlier definition, 124. And it's just a function and fv. And what it does is return the free variables of a formula for you. So again, let's look here. So free variable of Vn is just the set, just Vn itself. A constant doesn't have any free variables. The free variables of a function applied to some terms depends entirely on what the free variables of the terms are. It's just the union of their free variables. And free variables in this formula, S equals T, this equation, again, it's the free variables of the things on either side. And so it goes on through the other clauses. The free variables of a relation, again, like for a function, it's just the free variables of the components. And the free variables of not phi are exactly the same as that of phi. And if phi are as psi, it's just those of phi together with psi. And the clause, there's the last one, which has the kind of the most interest, is when you've got a formula phi, by putting a quantifier at the front, you then say, okay, that formula is no longer a free variable. So we remove Vn from the set of free variables of phi. So again, what we're doing is defining by recursion this function. In the first two lines, we define what free variable is fv is applied to terms, right? And then having done that, in the rest of the lines, we work out what the free variables are of formulae. Now, if a formula doesn't have any free variables, in the simple example I gave before, it exists v0 equals c, then we call it a sentence, right? When we interpret it in the structure, it's either going to come out true or false. And a term, again, is like a compound noun, or maybe just a noun itself if it's a constant term. It will represent some definite object in the structure once we evaluate all the components. So corresponding to sentences for formulae, we have closed terms for terms with no free variables. And the point of a closed term is that it identifies a unique element in the domain. There's no ambiguity, there are no parameters to fill in to work out exactly what thing it's pointing to. Okay. So let's look at some examples then here. So I've got a binary relation symbol, and it's got free variables v0 and v1 in it. Although I can see later on in the example, I changed the free variables to something else, v1 and v2. So let's see how the recipe works out. Right? By itself, R has got two free variables. So fv of R would be v0, the set containing v0 and v1. But over here, what I've done is first quantify over R using for all v1. This removes v1 from being a free variable. And then I do the same again with v0. So I've quantified over the only two free variables there are. So these variables are no longer free. So there are no free variables left in this formula. Right? It's become a sentence. Right? And here I've got a formula, and I've got in my relation now v1 and v2. So by itself, R has got free variables v1 and v2. But now I've quantified over using v0. So somewhat meaninglessly, I've quantified over a variable that doesn't appear in the formula. But nevertheless, it's still a perfectly good formula. Right? But the quantification didn't remove any free variables and left them there as where they were. this here has got no free variables because a constant term is closed and has no free variables in itself. We've quantified over the only variable there is. And I kind of leave you to puzzle out the rest that are here, right? What we've got here is kind of a compound system here. What have I got? You first have to kind of work from the, as it were, work from the outside in. I look at the free variables of the whole formula. And what I've done over here is I've stripped off the outer V0. Right? So the free variables of this, whatever they are the free variables of this minus V0, which I quantify to get there. Right? So now, what are the free variables of this? Again, I look back at the recursive definition of what's free variables of an implication. So it's the free variables of the antecedent together with the free variables of the consequent. That's what I've written here. Again, still not forgetting the minus V0. So now I look and compute what are the free variables of here. This part is V0, V1. Here there are no free variables left because I have used the quantifiers to bind the free variables that are there. So that's empty. And I subtract V0. So this just leaves me with V1. Okay, and the others are, I leave you to work out for yourself there. So those definitions are what I would have called, part of the syntax. So on the board over here, it's in stuff in the square box, right? Formal languages. It's all stuff about the syntax, the grammar, and the punctuation of the language, right? It's not about interpreting the language yet inside structures. And we'll recap that in a moment. So the idea, of course, is that when we look at formulae with free variables in, and we might want to assess this formula in a structure, I can't do that unless you tell me what you're going to assign to the free variables. Right? If you say V0 equals C, I can just shrug. I don't know what that's going to mean until you tell me what V0 is. So we need interpretations of the parts of the formula. We need some bridge mechanism that goes from a formula over to, say, a mathematical structure and picks out actual, real world mathematical objects, which we're going to assign to the variables in the formula. And at the same time, we need to assign what are the constants going to denote. Right? Constant is a noun, so it names something. Well, you have to tell me what that constant is going to name in the structure. And likewise, if in my language I've got a sort of binary function, you have to tell me what function that relates to in the structure. And likewise for binary or three-place or n-ary relations. So we're going to have to give a definition, and this is what Charles Morgan called an interpretation, right, of the things in our language in a structure or in any structure that we're trying to deal with. So this is in the next subsection that's here. I've called the interpretations valuations. Right? I've just made them slightly different from what Charles was thinking about. I think it's simpler to think of an interpretation really as a function that's extended. So, I mean, the idea here is okay, so we may have some structure. M, and maybe it's got some domain, and I'm going to write this for the domain of M. So I think of the structure as being a set of objects, and then there are going to be whatever the function symbols there are here, or the constant symbols are, and the relation symbols are all going to have corresponding objects in the structure. I've just written down one of each, but there may be, in a countable language, there could be countably many functions or constants or relation symbols. So I distinguish between the structure, which Charles was writing with a kind of a script M, and the straight Roman M is the actual set of elements. We might have something, maybe it's a group. Here are the objects in the group, and here's the group operation, and here's the group inverse, and here's the group identity. So this is good for a language where we've got a multiplication, a binary multiplication, a one-place function, and one constant. So again, this is the set of elements of the group. This is the whole structure, the set with its operations. And sometimes I write, I think in some of the exercises, I write also an A with an underline, which is to indicate there's a structure. Again, the set of elements plus the other data that's down there. So in definition 330, this is valuations. So this is W for M here. This is the set of little w's. So that basically little w is a function, and it goes from the natural numbers into M, a set of elements of M. Here. And the idea is just going to be, is simple. VK will be valuated or interpreted or valuated. That doesn't sound good. Valued. The valuation of VK. VK will be assigned. WK. So we've got infinitely many variables, V0, V1, V2, and so on. So this W takes care of how we're going to assign an object in M to VK. Okay, so that tells us how to map variables into the structure. The next definition assigns, so I just called it extended valuations. So I put a star up here, M here. Well, VKs, we've just said that's just going to be what WK is. Here's a constant from the language. That is going to be assigned whatever constant we've agreed that this C will be naming here. And now I need to know what it does to other terms. So we first inductively assume we know what we've got here on the term, the t's. We apply the function f here to the interpretation of the terms. up to Tn here. So again, if we were to look at this more carefully, it's an induction on the complexity of the term here. This has got a certain level of complexity, but it's higher than the complexity of the t's. So by induction, I assume, as inductive hypothesis, I've already defined what these things are. And then this clause tells me, well, the assignment to this is the F of the structure applied to the things that we already know here. So again, this is a definition by induction on the complexity of the terms. Here. And there is a useful device in 332 where we just look at variations. So if I've got a function w that goes from n into m, it's one of these. And I pick an object I just pick some object in the structure P. Then here's the variant one. It's also in Wm. But what it does, it's exactly the same as my original W, except that on I it returns P rather than whatever W of I was before. So WPI here is P. Sorry, if J equals I. But otherwise, sorry, start again. WPI at J, this is just going to be WJ if J is different from I. On the other hand, if J equals I, then this is going to be P. So it's just a piece of notation for this variant that we're here. So it does exactly the same as what W does, except in the ith place, it's going to return P. Again, let's see an example on the next page. Example 333. Now I've got the natural number structure here, n. And I presented the natural numbers. Here's the set of natural numbers. And what do we have? We have two binary function symbols here, plus and times. 0 is a constant symbol. And here's a one place symbol. This prime denotes successor or +1. So here's a valuation, right? I mean, this is all simple stuff, really. We're going to assign to variable v4 23 and to variable v6 2. So we now compute these extended valuations. And actually, 0 prime prime is always going to get valued at 2, irrespective of what W does, because there are no free variables in 0 prime prime. The symbol 0 will be assigned the number, well, naught, and then the prime prime is going to be a repetition of the function that we'll assign to be the successor function. So it'll just add 1 twice. On the other hand, if I look at this valuation here, the extended assignment to extended valuation to this formula, right, is, well, I apply the function in the structure, which is times n here, to the terms which I first evaluate. And we've said that this valuation is going to send 23 to 4, and it will send 2 to 6. So we end up with a number in the structure of 46. So this is all very mechanical, right? Our definition over here of, let me emphasize, of free variables here, this is something that's entirely algorithmic, right? I mean, if you were writing a program to deal with formal languages like this would be completely simple to just write a program that'll compute what the free variables of a formula are. So let's once more go over here, the definition of, we step over the divide now, and we look to see what, how we define meaning, how we can assign meaning to our formulae. So again, this is called the satisfaction relation. It's closely related to something called the Tarskian truth definition. And indeed, this is something that Tarski, first Polish logician, and late 20s and early 30s drew up, was how to define mathematically what it would mean for a formal language formula to be true in a structure. So the idea is essentially that it's a relation around this kind of funny double turnstile thing. On the left, you have a structure appropriate for some language. You've got a phi, which is a formula of the language, which may have free variables in. And we use the assignment function to tell us what the free variables will be assigned in n. So we've defined what the assignments of terms are. We now want to work out, with that assignment of terms, which formulae are going to hold in the structure. Well, here an equation will hold if, well, to be true, it better be that what you assign to S and what you assign to T better be the same, which is what we have here. If a relation is going to hold, for example, R might be something like a less than, right? It might say T1 is less than T2, right? Just as a piece of syntax, right? Well, it better be that whatever we interpret this letter as in a language, it better be that the interpretation of T1 is, well, in the relation R to the interpretation of T2. Right, that subscript there should have been a superscript. So we look at whatever relations we have, right? And if I've got here R, it's an n-ary relation here. I look at the evaluations of the n terms that I put in, and I see if that actually holds, right? If that's one of the n-tuples which is inside the relation of m. So M will think then that not psi comes out true under the assignment W, right? Precisely when its opposite does not come out true. In other words, if it's not the case that M psi comes out true under the assignment W. And for an implication, W will make psi as chi come out true if whenever it makes psi come out true, it makes chi come out true, which is what is written down here. And then the thing that gives us a bit more in terms of meaning is the universally quantified formula here. Now the idea is, okay, let's imagine that this formula is saying something about VK. For example, VK is something that's free inside phi. Right? What this then, with the for VK at the front, says, well, no matter what VK is assigned, it's going to come out true. And that's actually all that's said on the right-hand side. It says whatever you pick from M, if I evaluate VK as A, which is what this valuation does here, all other things being kept the same as in W, then it comes out true. So the only thing that's been varied between W, A for K, and W is what it returns on K. So if we allow it on K to vary over all the possible objects inside M, and if all of these come out true, then, hey presto, we've got that the intended interpretation here will deem that to have come out true.